So this is artificial neural network that powers the decision making for the snake game. Now let's understand these individual layers. Let's start with the input layer. So input layer represented by these red nodes, where each node represents one feature. Okay, and these features encode the state of the snake and its environment. So basically, state of the game. So in a game, we'll have walls, we'll have food, and we'll have the snake. So all of these, like walls, snake, and food, will be represented by the features. And for this snake game, we'll have 16 features. Why 16 features? That we will see when we implement the agent class. For now, just understand that this input layer represents the state of the game, and each state will have 16 features. What are the features? The position of the snake, whether there is a danger in each direction, what is the current direction of the snake, the location of the food relative to the snake. So collectively, all these features represents the state of the snake, and will pass the state of the game to the input layer. So in our program, we'll have 16 nodes. These are also called artificial neurons. Now let's talk about the hidden layer. So hidden layer represented by these blue nodes in the middle. It's a simple snake game, so we'll have only one hidden layer. So this layer processes the input features using weights and biases. It applies non-linear transformation, activation functions, learn complex patterns and relationship. So for this snake game, we are going to use rectified linear unit as the activation function, in short, RELU. Now the output layer. So in our output layer, we'll have total 4 nodes. Each of these nodes corresponds to a possible action that a snake can take. So a snake can move left, a snake can move right, a snake can go up, and a snake can go down. So each node corresponds to the one direction. So total 4 nodes. So the network predicts a Q value for each action, which represents how good it is to take that action in the current state. The action with the highest Q value is selected by the agent. And every node in the input layer is connected to the every node in the hidden layer, and every hidden node is connected to the every output node. These connections have weights which are adjusted during training to minimize the loss and improve the network performance. Now let's quickly read what Wiki says about artificial neural network. So ANN consists of connected units or nodes called artificial neurons. So these are artificial neurons which loosely model the neurons in the brain. Artificial neurons models that mimic biological neurons. So these are connected by the edges, which model the synapses in the brain. Each artificial neuron receives the signal from the connected neuron, then processes them and sends a signal to the other connected neuron. So for example, this neuron takes the information from the neurons here, process them, and pass the information to the output layer. The signal is a real number, and the output of each neuron is computed by some non-linear function of the sum of its input called activation function. We'll create a new class here. Let's call it as agent.py. Now let's create our artificial neural network class. This will inherit from ANN.module. ANN stands for neural network. Okay. Now before we proceed, we need to install the PyTorch library. So we'll do pip install torch. Okay, PyTorch is successfully installed. Import torch.nn. Okay. Now let's create the constructor, and we'll have state, size, and action size. Okay, so remember the state size input and the action size output. Let's call the super constructor. Now let's have fully connected layers. So we'll have 2 fully connected layers. So let's see one, and ANN dot linear state size 64. and second fully connected layer 64 to action size. So let's understand this. We have two fully connected layer which takes the input as a size of state size and the output 64. That's the number of neurons in the hidden layer 64. I'm going with 64 neurons in the hidden layer. You can try 128, 256. General practice is to choose number of neurons in the hidden layer is 2 power n, but again, there is no fixed rule. So you can try with 32, 64, 128, 256. I think it's a simple snake game, so 64 should be good enough. And the second fully connected layer, the hidden layer 64 neurons to the action size. So as I said earlier, we'll have 16 as the state size and the action size is 4. So we'll have 64 neurons in the hidden layer, 16 in the input and 4 in the output. So first fully connected layer pass the data from the 16 neurons to the 64 neurons in the hidden layer, and the second fully connected layer pass the data from 64 neurons to output layer, which is 4 neurons. Okay, so this is important to understand. So again, the state size, the size of input layer, which corresponds to the state representation of the game. Action size, the size of the output layer representing the number of possible actions that a snake can take. Okay. FC1, this is a fully connected layer with the state size as input and 64 hidden units as output. FC2, another fully connected layer with 64 inputs from the hidden layer and action size, the output. Now let's have forward pass, and this takes state as an input. So let's understand the forward pass. The forward method defines how the input data flows through the network. So this is the first transformation. The input state is passed to the first fully connected layer, FC1, which performs the linear transformation and produces the 64 features. And then the activation function. So output of FC1, the fully connected layer 1, it passed through ReLU function, rectified linear unit activation function, and then at the end, output layer. The activation features are passed through FC2, the fully connected layer 2, to produce the final value for each action. Okay. Now with that, we have successfully created the artificial neural network that is the brain for the snake.